Alright, and welcome back. In this video, we're going to continue talking about the fundamentals of physics properties and measurements. We're going to talk about data analysis. When we're making measurements, we need to talk about the difference between what an accurate and precise measurements are. Precisions are how close your measurements are to each other, while accuracy is how close your measurements are to the actual value. So something that is low accuracy and low precision are going to be measurements that are really bad. You're kind of spread out all over the place and you don't have anything that is like actual near the values that you need to be looking for. Low accuracy, high precision, all right, pretty much all of your measurements are going to be far off from where you actually want your measurements to be. But they're all going to be very concise in terms of where they are relative to each other. All right, now this is something that is okay because to have in an experiment, because you're going to have errors that maybe you can't account for, like air resistance. All right, so you might not be getting the exact speed measurements of something, but they're all going to be pretty close together to each other. Now, high accuracy, low precision, all right, these are going to be measurements where you might get one really lucky where you would really get the exact value, but all of your measurements are kind of all over the place. And then high accuracy, high precision is ideally what we want, a lot of measurements that are right on target. And so if we're using a bullseye analogy, your arrow's hitting the target really well. In that first one, D, high accuracy, high precision, really poorly, low accuracy, low precision. In the second one, then C, high accuracy, low precision, and then B is the last one, low accuracy, high precision. Now there's always uncertainty in measurements. We could always be more precise if we have better equipment, which usually is a lot more expensive. This uncertainty carries over through the calculations, and sig figs help us do this. Now, in my class, I don't have my kids necessarily calculate in significant figures, but we do measure them in the lab with significant figures. All right, so I'm not worried about calculating in sig figs. However, you must make sure you're recording it. All right, so if your friend runs 100 meters and you use your stopwatch to time them and you see that their time is 11.40 seconds, a very respectable time for a high school student. Now in your data table, you're going to record this as 11.40, not 11.4. So don't drop the zero. You actually have that value of certainty where you know, okay, this is the actual next value. And don't add any extra decimals if you can't tell what they are. This particularly is important for like meter sticks, where the actual line might be in between the two actual measurement lines, as we see here. All right, so both A and B are right on their values, so we would say that's 13.5 centimeters and 11.1 centimeters. Now D, C, and E are all kind of in between the different hash marks, and so we're going to use the lower value that we know. Hey, guess it is. All right, so C is going to be 14.3 centimeters, 12.2 for D, and E is going to be 12.6 centimeters. All right, so this kind of gives you a rundown what happens when you are putting numbers together mathematically based on certainty. All right, so precise numbers added together will just give you a slightly less precise number. Anytime you're doing anything with garbage numbers, you're going to just get worse and worse data. Unless you have garbage times 0, which is a precise number, which is 0. So when we're analyzing data, we want to find relationships to create equations. So we can use this as a predictive tool. So extrapolation is when you're going to make predictions outside of your data range. So if you are measuring how far something goes in a certain amount of time, you're going to use your data to estimate how far it would go and at a time interval that's greater than what you're measuring. And Interpolation is where we're going to make predictions inside your data range. So if it takes this, you're measuring a certain amount of time it takes to go certain distances, well, you're going to use your data to be like, well, this is how long it took to go to X distance, which was not a number you were specifically measuring. All right, so if you're making graphs, all right, you want to make sure they're large and neat enough to read. Make sure the graphs have titles, axes, labels correctly on the Y versus X axis, such as height and range, or range versus height. You want to make sure that they're labeled with the proper units as well, a scale that is readable and fits the data. Points are plotted correctly, which most of my students, we use different computer programs like Google Sheets and Excel, so there's no excuse there. And we want to make sure we add appropriate trend lines to look for trends in the data. All right, so usually data, when it seems linear, a line of best fit can be used. It should be pretty close to going through all of those points. You might have a few above or below in equal kind of spacing. All right, so then we can create an equation from that trend line and use that as a predictive tool. All right, so here is a linear or directly proportional relationship. We have a straight line where the equation of that line is y equals mx plus b. So as one measurement is increasing or decreasing by a factor, the other will change by the same factor. While inversely proportional kind of gives you a hyperbola. All right, so that equation is going to be y equals k divided by x, where k is going to be a constant. So your variables are x and y. Now here, as one measurement is increasing, the other is doing the opposite. So if you are doubling x, you're going to actually cut y in half. So if x goes up, y goes down by the same amount. Now, a quadratic relationship we'll also see quite often in physics. It gives you a parabola, where the general equation is y equals k times x squared. Again, k is going to be some sort of constant. So if x is increasing by a factor of 2 because it's squared, 2 squared is 4, so y is going to increase 4 times as much. Alright, so that's it for that video. We'll see you back here soon.